In this video, we're going to talk about one of my favorite reactions called the Diels-Alder reaction. And in essence, a Diels-Alder reaction is a 1,4 addition reaction of a conjugated diene with what we call a dienophile. And a dienophile is simply a pi bond. This could be from an alkene or from an alkyne. And we'll look at examples of both of them. So the cool thing about the Diels-Alder reaction is that it produces a six-membered ring. So if in the simplest scenario I take 1,3-butadiene and I react it with a dienophile, namely a pi bond, so we'll start off simply with ethylene, right? Notice that the 1,3-butadiene is in the S-cis formation. So I'm reacting it with ethylene, which is my dienophile. And what happens is we get an addition reaction. So one of the pi bonds from the 1,2 carbon reacts with the alkene. So in this instance, the conjugated diene is behaving like a nucleophile, like we saw with the other addition reactions, and the alkene is behaving like an electrophile. Now, as electron density moves toward that the dienophile, it now becomes electron rich, which in essence then shifts it from an electrophile to a nucleophile, and at this stage it can then attack the butadiene at the 4 position. So notice we're getting a 1,4 addition. So we're adding at the 1 carbon of 1,3-butadiene and at the 4 carbon of 1,3-butadiene. And then at this stage, what happens with the last double bond on the diene is that it actually migrates in between the 2 and the 3 carbon. The result is, and if you can kind of visualize what's happening at that with those pi electrons, is we're essentially redistributing those pi electrons, and we're going from a pi bond to now these sigma bonds, and then the pi electrons on the between the 3 and 4 carbon are actually moving down, and the result is a ring and the movement of one of the pi bonds, and so we get cyclohexadiene. I'm sorry, cyclohexene. So here I have an example of 1,3-butadiene reacting with this dienophile, and again, if I think about numbering it 1 through 4, I see attack from the diene to the dienophile, and then those pi electrons are going to attack the 4 position, and then the pi electrons between C3 and C4 move to in between C2 and C3. And we end up with our cyclohexene, and of course, since the dienophile had 2 carboxylic acids group coming off of it, those are also still attached. So let's look at some characteristics of the diene and the dienophile. So first, the diene. The key thing about the diene is that it must be able to adopt the S-cis form of that structure. And so if it can't, so in this particular example, notice because of the rings, those rings are going to really inhibit rotation to occur, and therefore this particular conjugated diene has to stay in the S-trans formation, and therefore this type of diene is very unreactive toward Diels-Alder reactions. Likewise, something like this. Now, it looks linear in nature, but this is the ZZ stereoisomer of, let's see, what is this, 2,4 hexadiene. And so that ZZ stereochemistry makes it unreactive. And you might say, well, why is that? Well, again, here we have the S-trans conformation, and of course it is free to rotate to the S-cis conformation, and yet when I do rotate it, what I end up getting is a structure that looks like this. And you see that those methyl groups actually come in very close proximity to one another, and so we have this steric strain that is occurring, which really inhibits that S-cis formation. And therefore, this is much greater than 10 kilojoules per mole higher in energy, and it really doesn't form, and therefore this particular diene is unreactive toward Diels-Alder reactions. However, if I have the E stereoisomer, EE stereoisomer of the same diene, it is very reactive. And the reason for that is because if you notice when I rotate about that single bond, I get a structure that looks like this, where the two methyl groups are actually away from one another. Likewise, I can look at cyclic conjugated dienes, like this structure here, and you see that in this particular structure, in essence, everything is in the S-cis conformation, and therefore it becomes very highly reactive toward Diels-Alder reactions. All right, so now let's think about the Dienophile. And in general, reactions take place most rapidly when you have a Dienophile that has electron withdrawing groups coming off of it. So one of the things that you have to be able to discern is whether or not a group is electron withdrawing or electron donating. And this is probably one of the key features. So for example, when we have anything that has a carbonyl attached to it, we know that carbonyls are very polar. The oxygen's withdrawing electron density away from the carbon, so the carbon takes on this partial positive charge, and so it's seeking out electrons. And therefore, anything that has a carbonyl, carboxylic acids, esters, amides, acyl halides, ketones, are going to be electron withdrawing groups. Also, nitriles are electron withdrawing groups. The nitrogen withdraws electron density away from the carbon, making that carbon partially positive charge. We can have groups like nitro groups on. So if you draw out the Lewis structure, remember the nitrogen has a positive charge on, a formal positive charge on it, and therefore it is a strong electron withdrawing group. And because of these features, remember the dienophile is an electrophile. So, and it's that pi bond that is electrophilic, it's accepting electrons. The way that we make it a better electrophile is by putting groups on that withdraw that electron density. The other feature with dienophiles is their stereochemistry. So, we're talking about an alkene, and that alkene can have cis or trans stereochemistry. And the thing to remember in a Diels-Alder reaction is that the stereochemistry of the dienophile is retained. And so if you start with an alkene that is cis in its stereochemistry, then the product ends up, that cyclohexene ends up where the groups are cis to one another. So for example, here I have 1,3-butadiene reacting with my dienophile, and notice the carboxylic acids are cis to one another, and therefore when I draw out my product, they are the two carboxylic acids are cis to one another. So let's look at a little bit more complex system, and that is the reaction of cyclic conjugated dienes. And we're going to see why they're a little bit more complex in very shortly, because here I'm taking cyclopentadiene, which we know is very reactive simply because it's locked into that S-cis conformation. And when I react it with a dienophile, which I've labeled, some group coming off X, doesn't really matter what it is, and I draw out that structure, if I think about that cyclohexene structure, I'm still missing something. What am I missing? Well, I'm missing this methylene group right there. So if I think about where that methylene group is, it's still attached to carbon 1 and 4. And so it's actually right here. And if I think about the structure that I make in this instance, it's actually a bicyclic structure. So how do we draw bicyclic structures? Do we draw them like this? Absolutely not. All right, we don't draw it this way. And the reason for this is because if I look at that structure, I know that there's going to be a lot of angle strain there, right? So cyclohexene tends to pucker into either, it tends to form chair conformations or boat conformations. When you have that bridge forces that conformation to be more of a boat. So we draw it like this. Right? So I'm going to draw it kind of at an angle. So here's my boat, and then that methylene group is going to be right like that. And then I have my double bond, right? So it takes on this puckered shape. And this is called norbornene. And I like to think of this as an upside down boat, and that methylene group would be the anchor of the boat. So if you flipped it around, you see, oh, I have a boat, and then that methylene group would be pointing down as its anchor. So let's go back to that general reaction where you have cyclopentadiene reacting with a dienophile, and so we would draw it like this. But notice, when we talk about chair and boat conformations, there's two positions where the X can actually go to on that ring. So I've drawn those two positions. The one on the left-hand side is called the exo position. And so if you think about that, it's closest to that 5-membered ring. And then the one on the right is the endo position, and it's closest to the complete 6-membered ring, where the X, the electron withdrawing group, typically is in that pocket. So you have two distinct pockets, and you have to think about what's going on in those two pockets. It happens that the endo stereoisomer is the one that's actually favored. And if we look at an example, we can kind of determine why that endo product is the favored product. So here I have cyclopentadiene, and it's reacting with cyanoethylene. And so here's my product, my two products that I get, where the cyanide is endo versus exo, right? And in the endo position, I see that 60% of it is formed, in the exo 40% of it. So I get a slight excess amount of endo product. And the reason for this is, if we think about the molecular geometry, the orbital geometry of the cyclopentadiene, as it forms an overlap with the pi orbital of my dienophile, the cyanide also has pi bonds. And so if I draw out all the pi bonds of this molecule, which, I have 8 p orbitals that have the potential to overlap. Now, when that molecule comes in to form that cyclic ring, right, I know that I'm forming a bond between the orbital on C4 and the dienophile, and the orbital of C1 and the dienophile. But the orbitals of the the nitrile can actually start to overlap with an orbital of C2 or C3, right? And it's this overlap of the homo-lumo, we say interaction, that enhances the formation of the endo product. So here are a couple of examples, and keep in mind that stereochemistry is retained, I said, of the Dienophile. A common mistake that's made is students say, "Oh, okay, well the groups off of the Dienophile have to be in the endo position." Well, if they're trans to one another, which we have these nitriles that are trans to one another, then they're going to be trans to one another in the product. And so when we draw the product, that product looks like this, where one of the cyanides is in the endo position, but the other one has to be in the exo position because, again, stereochemistry is retained, and therefore it has to be on the opposite side of the ring than from the other cyanide. Right? So if I start with trans, I end up with trans stereochemistry. Now let's look at what happens when cyclopentadiene reacts with an alkyne. Again, same type of reaction, but this time, now we have 2 pi bonds. One of the pi bonds forms a sigma bond. The other pi bond is actually left over. And so you notice that we get a diene. And of course, in terms of molecular shape, we know that alkenes are sp2 hybridized, and so this is actually a planar geometry. So the carboxylic acids are neither endo nor are they exo. They're simply trigonal planar geometry.